Okay, here we are back again. Once again, as a reminder, I'd like to tell you that we're covering a great deal of material, which I'm sure all of you realize, in a very cursory fashion, in a sense. And once again, I'd like to encourage you to try to squeeze out of this material just a little bit of physical understanding, kind of a physical feel for what's going on. The details you can fill in later on, the equations you can fill in later on. If anything, I'd kind of like you to get a little perspective on things, maybe a little philosophy on things. And so that is what I'd like to see synthesized out of our discussions here today. We have a little bit of unfinished business carrying over from our last hour, and that is our discussion on viscous interactions. I'd like to go back and simply repeat again that the governing correlating parameter for viscous interactions in terms of pressure distributions is this chi-bar parameter. Let's refer again to figure 7.4 on page 313. Let me remind you that we're looking at the variation of pressure on a flat plate in a hypersonic flow. And what is this pressure plotted versus? It's plotted versus chi-bar. That's the only thing that's needed, because that is the only thing on which this pressure depends. And so what we're really, and let me remind you again, what is chi-bar? M infinity cubed over the square root of the Reynolds number times the square root of C, the rho-mu ratio. The one way to interpret this kind of picture is as follows. Imagine, and I'll draw a picture here, imagine that you have just a single flat plate. Okay, here's a single flat plate with some free stream, say V infinity, and X is measured from the leading edge. Now remember that the Reynolds number is equal to the density times the velocity times X over mu. And the chi-bar parameter is equal to M infinity cubed over the square root of the Reynolds number times the square root of C. So what happens if we start out here at the back of the plate and we start moving forward towards the leading edge? As we move forward towards the leading edge, X gets smaller. As we move towards the leading edge, X becomes smaller. If X becomes smaller, the Reynolds number becomes smaller. And if the Reynolds number becomes smaller, chi-bar increases. And so effectively, for a single flat plate in a single experiment, if you have a number of pressure taps along the surface of the flat plate, each one of those pressure taps corresponds to a different value of chi-bar. And so when we look at data plotted, as we see it here on P over P infinity as a function of chi-bar, you can kind of visualize this basically is just running along the surface of a flat plate. And as we go out here to higher and higher values of chi-bar, we're just moving closer and closer to the leading edge of the flat plate. Okay, but in any event, we see here experimental data from different experiments, different Mach numbers and Reynolds numbers, and those data all correlate as a function of chi-bar. We see the fact that these equations we were looking at in the just before the break, which represent these curves on the graph, are reasonable representations of the viscous interaction effect on pressure. So in terms of the pressure effect on hypersonic on the surfaces of hypersonic vehicles, the influence of viscous interactions is to increase the pressure, and the pressure in terms of the pressure ratio P over P infinity is correlated by this viscous interaction parameter chi-bar. Very important parameter in high-speed, high-altitude hypersonic applications. Now, that's not the whole story. Let me give you a little bit of, corollary to this study, to this story. And it has to do as follows. Now, I'm going to use we'll draw this out on the pad of paper here. We said that P over P infinity was correlated by chi-bar, which is M infinity cubed over the square root of the Reynolds number, square root of C. Okay? Now, what about pressure coefficient? Do you think that's correlated by chi-bar? If the pressure is correlated by chi-bar, wouldn't pressure coefficient be correlated by the same thing? How many people think yes? Would this pressure coefficient also be correlated by chi-bar? Question mark. What do you think? Anybody want to vote? How many people feel the pressure coefficient ought to be correlated by chi-bar? Don't be bashful. Oh, 1, 2, 3, 4. Majority, looks like. How many people feel it's not correlated by chi-bar? 1. Well, here in the United States, it should be correlated by chi-bar because the majority vote wins, right? So by majority, it should be. However, let's take a quick look. Let's look at the pressure coefficient, C sub P. P minus P infinity over the dynamic pressure. Let's look at the dynamic pressure, Q infinity. By definition, it's 1/2 rho infinity V infinity squared. Okay? Let me take this and multiply and divide by gamma times P. Gamma P infinity over gamma P infinity times 1/2 rho infinity V infinity squared. Now we'll carry this on down here. This gamma P infinity over the rho infinity, that's the square of the speed of sound, isn't it? And so this gamma P infinity carries on, divided by 2, that's this. We have V infinity squared. Gamma P infinity rho infinity is A infinity squared. So we have gamma P infinity over 2 Mach number squared. So what does that say? When we go back to our pressure coefficient, we'll just continue this on. When we go back to our pressure coefficient now, which is P minus P infinity over Q infinity, is really P minus P infinity divided by gamma P infinity over 2 Mach number squared. Or the pressure coefficient can be expressed as 2 over gamma M infinity squared P over P infinity minus 1. This is the thing that's correlated by chi-bar. But now we're dividing it by an M infinity squared. Conclusion, the pressure coefficient should be correlated more by something like M infinity to the first power over the square root of the Reynolds number, and that is indeed the case. So please keep in mind that this chi-bar parameter is just, and I'll put this back on the monitor, this figure that we were looking at, this is just pressure ratio, P over P infinity. It's not the pressure coefficient. Indeed, the pressure coefficient is more correlated by, and I'll show this on here, the pressure coefficient, according to equation 744 on page 315, is correlated more by M infinity, or the square root of the Reynolds number times square root of C. That's called V bar. That's about all that I'm going to say, in essence, on viscous interactions, because we need to move on to other aspects of hypersonic viscous flows. You'll find in your notes more details associated with viscous interactions, and it's worthwhile for you to take the time to look at those at your leisure. What I want to do now in the next few minutes, so let's go back to our roadmap. We're talking about hypersonic viscous flows. We have been down here talking about strong and weak viscous interactions. I want to drop down to this milestone in our roadmap and spend a little bit of time talking about modern computational methods, and in particular the solutions of Navier-Stokes equations for hypersonic viscous flows. What we're talking about here, and again, by the way, this is the subject of Chapter 8 in your notes, and I'll just put this up on the monitor. Chapter having to do with the computational fluid dynamic solutions of hypersonic viscous flows. I want to draw just a few highlights from this consideration. We've already talked about one way to analyze a hypersonic viscous flow, and that is to solve the boundary layer equations. Now, the boundary layer equations work fine when you're dealing with relatively thin boundary layers. But when the boundary layers become thick, and especially when they become as thick as the entire shock layer, you've got to do business in a different way. Now here's a different way of doing business. There are systems of equations, which I'm going to just point out to you. This is on page 337. There are systems of equations which are more accurate than the boundary layer equations. One notch up from the boundary layer equations is something called the viscous shock layer equations. And these viscous shock layer equations are nothing other than the boundary layer equations, with the exception of the partial P respect to y equaling 0 being thrown out. with the exception that you now have a Y momentum equation that allows you to calculate a finite pressure gradient through the viscous flow in the normal direction. Then the viscous shock layer solutions have been, in that context, have been used very extensively over the last 20 years to calculate hypersonic viscous flows over blunt nose bodies, high temperature flows, and we'll even refer a little bit later on before the end of today, I hope, to some viscous shock layer solutions wherein we are dealing with high temperature chemically reacting flows. But these viscous shock layer equations are one notch up from the boundary layer equations, that one notch having to do with the normal pressure gradient through the flow. Now another notch up from the viscous shock layer equations are the parabolized Navier-Stokes equations. Now these are the full Navier-Stokes equations where all the terms, all the viscous terms in the x direction have been dropped out in the flow direction. You look at your Navier-Stokes equations and you have viscous terms in the flow directions, derivatives in the flow directions, and you put all those equal to 0. And you keep the viscous terms in the y and the z direction. The resulting system of equations that you get are the parabolized Navier-Stokes solutions. And then finally you have the full Navier-Stokes solutions, full Navier-Stokes equations, the ones that we looked at during the last hour. So you have this kind of hierarchy of viscous flow solutions that you can attempt in order to get information to calculate viscous flows, and all three, and also the boundary layer equations, you want to say, and therefore all four, are used in hypersonic flows. All these three approaches here have been used extensively to study hypersonic flows. Now, I want to concentrate back up just for a minute. Viscous shock layer equations, and we'll put this back on the monitor. For the viscous shock layer solution, the viscous shock layer equations, these have been used over the last 20 years to study hypersonic viscous flows over blunt nose bodies. In more recent times, the parabolized Navier-Stokes solutions have been used because they contain a few more terms and they have a little more accuracy. And as a matter of fact, the parabolized Navier-Stokes equations, computer programs for solving the parabolized Navier-Stokes equations are extensively used today by industry and by government. And I want to talk about these in terms of some of their physical solutions and some of the problems they have, just for a few minutes. We're going to concentrate on the parabolized Navier-Stokes equations. And I'm going to do this by killing about three birds with one stone. We're going to refer to a figure here on page 347. It's going to take a few moments here and I'll walk you through. We are looking at pressure distributions over slender blunt nose cones. Let me draw a picture. We'll have a sort of a slender cone here with a blunt nose on it. And we're going to look at, say, pressure. This is the x direction. We're going to look at pressure distributions as a function of x all along the surface of this blunt nose slender cone. So this is what we have here. A pressure as a function of distance x divided by the nose diameter over this slender blunt nose cone. First of all, in this figure are experimental data for such pressure distributions, taken for a Mach number of almost 6, a fairly high Reynolds number, about 15 million. Small angle of attack, about 4 degrees. The cone angle, half angle, is 6 degrees, so it's really a slender cone. Now, if you calculate m infinity cubed over the square root of the Reynolds number, you get something like 0.054. I didn't bother to put in the square root of c here. This is effectively chi bar. This is a very low value of chi bar. You would, for these conditions, therefore, you would expect to see very minimal viscous interaction. So visualize now all the curve here, these data here. This is basically a case where the viscous interaction effects are not important. Okay, so that's one thought. Second thought, again, experimental data. These symbols here represent experimental data, and they represent experimental data, first of all, along the windward streamline, along the windward surface of the cone. Now, by definition, if you come back to me here for a minute, imagine this pen is at an angle of attack, flow coming in this direction. The windward surface of the cone is the bottom surface of the cone. The leeward surface of the cone is up here on the top surface of the cone. Okay? Now if we go back to this figure, this is the pressure distribution on the windward surface at exactly the meridian plane where phi, and I'll draw in phi here to make things, in this particular case, if this is the back of the cone, we're measuring like phi in this direction, and the cone is at an angle of attack alpha. So phi equals 0 degrees would be right on the windward, most windward ray. That's where we have our highest pressure. Now as we go around the cone, 45 degrees we get this, and 135 degrees, and finally 180 degrees. This is on the leeward surface on the back ray of the cone. Okay, now let's see what's happening. Those are experimental data. There are two sets of calculations made here. Two sets of calculations. One is called, here's a solid curve, is called 3dV. What that is a three-dimensional inviscid flow field calculation of the flow over the cone matched to a conventional classical boundary layer on the surface of the cone. So this is the old standard way of doing business, where you calculate a flow field around the cone for using an inviscid flow, and then you tack onto that inviscid flow a boundary layer along the surface. And from this calculation you get a pressure distribution that looks like this. Now, the dash curve is a solution of the parabolized Navier-Stokes equations. This is a far cry from a boundary layer solution. This allows for pressure gradients in the normal direction. This is carrying a lot more viscous terms than the boundary layer equations. The parabolized Navier-Stokes equations, a much more accurate representation now of the viscous flow. Now when we look at these pressure distributions, we look at the calculated results, we see two things. First of all, the calculations agree pretty well with the experiments. And secondly, there's very little difference between the conventional inviscid flow boundary layer approach, the 3dV, and the parabolized Navier-Stokes solutions. Very little difference. Okay, now, so what that says, for these kinds of conditions, the kind of boundary layer calculations we were talking about during the last hour make plenty of sense. Reynolds number is high, thin boundary layer, relatively moderate Mach number, 6, makes plenty of sense. Okay, let's go to another case. This is the same scenario, except now we have a much higher Mach number, close to 10. The Reynolds number is a lot smaller, about 500,000, and this m infinity cubed over the square root of the Reynolds number is a lot bigger. Now this right away tells you that for this case we are going to have some significant viscous interactions. Now, keep that in mind. We're going to have some significant viscous interactions. Now let's go back and let's see what we have. What are we comparing here? This is our pressure as a function of distance along the blunt nose cone. We have experimental data along the windward streamline and the most leeward streamline. And we have our two sets of calculations. Now the conventional boundary layer calculation, the 3dV, the inviscid flow with the boundary layer calculation, solid curve here, gives us very poor agreement, especially on the leeward side, with the experimental data. Pretty poor agreement here too on the windward side, except for these points here. On the other hand, the parabolized Navier-Stokes solutions agree fairly well with the experimental data. Moreover, there's a big difference between the parabolized Navier-Stokes and the actual boundary layer type calculations. That difference is there in part due to the viscous interaction. What's happening here? The boundary layer equations are not inherently properly taking into account the viscous interaction. But the parabolized Navier-Stokes solutions are, because the parabolized Navier-Stokes solutions are treating the entire flow field between the body and the shock wave as totally viscous. And there is nothing magic going on inside that calculation, no switch in the computer program that is turned on and said, let there be viscous interactions. It doesn't happen that way. When you deal with the, and let me draw a picture here. Here's our blunted cone, and it's at hypersonic speeds. And I'm going to draw the shock wave here over this cone. It's an angle of attack. This whole shock wave, the whole shock layer between the shock wave and the body, when you deal with the parabolized Navier-Stokes equations, the whole thing is being treated as a viscous flow, all the way from the body to the shock wave. There is no special consideration of a boundary layer, no special consideration of an inviscid flow. The whole thing is viscous, at least insofar as the equations are concerned. And so what about viscous interactions? The effect of viscous interactions comes out in the wash automatically in this type of solution. And so the parabolized Navier-Stokes equations are calculating in a reasonably proper way the viscous interactions. And we see that there's a big difference here. This big difference translates into a particularly big difference in an axial force coefficient. Here's a plot of the axial force coefficient as a function of angle of attack for this cone. And same scenario, experimental data up here. The boundary layer calculations are down here, but the parabolized Navier-Stokes calculations agree very well with the data. And again, it's an indication of the following thing. In hypersonic viscous flows, especially in regions where you have to worry about viscous interactions, that means the boundary layer is getting to be thick. That means you ought to start thinking about making your flow field calculation in such a way that you're allowing the entire flow field to be viscous. And the parabolized Navier-Stokes equations will do that for you. And therefore, once again, the viscous interactions come out in the wash. Whatever effects you're going to have there from viscous interactions, it comes out in the wash. You don't do anything special to bring those things about. Okay, now that's parabolized Navier-Stokes equations. I might point out to you that there's a problem with these parabolized Navier-Stokes equations, and that is the fact that since you've thrown out these derivatives in the x direction, they don't allow you to calculate a separated flow in the streamwise direction. That's a real weakness. They do allow you to calculate a separated flow in the circumferential direction around the body. Here's a case in point. This is essentially a biconic configuration that's been studied for entry applications into foreign planetary atmospheres. And the parabolized Navier-Stokes equation has been used to calculate the flow field over this biconic. If we go in and look at, if we cut this body by a perpendicular plane, like I cut it with my hand, and we look at the top view of one of these cuts, when this body is at angle of attack, you have the flow, the cross flow coming around. You know, the bottom of the body is way down here, and the flow is curling around this body at angle of attack and going off in this direction. And we have a cross flow separation zone here. That is calculated. This is a parabolized Navier-Stokes calculation, and it does allow you to have separation in the cross flow direction. But it just doesn't give you separation in the streamwise direction, and that unfortunately is one of the major weaknesses of that calculation. Now, finally, let's wrap up our viscous flow discussion here with a quick discussion of the full Navier-Stokes equations. And you can find this in your book beginning on page 353. We're going to be dealing with full Navier-Stokes solutions. And here are the governing equations. These are the Navier-Stokes equations, again, with the unsteady terms. What I'm going to show you here are results from a time-marching finite difference solution of the complete full Navier-Stokes equations. Continuity, momentum, and the energy equation is on the back page. There's the energy equation. A time-marching solution in the same philosophy that I mentioned earlier today, where we will take these unsteady Navier-Stokes equations, and we'll wait for those to come up. We will solve for the time derivatives and advance the flow field in steps of time using these time derivatives until we go out to a steady state. The application for which we will make this will be rather interesting looking hypersonic configuration, the X-24. Here's the X-24. Now, also what I'm going to show you happens to be a rather history-making calculation, because I'm going to show you the results which represent for the first time in history that the complete full Navier-Stokes equations have ever been used to solve for the complete whole flow field over an airplane configuration. And it just so happens that it applies to a hypersonic case, about Mach 6. This calculation was made by Joe Shang at Wright-Patterson Air Force Base about four years ago approximately now. And as I say again, it was for the first time in history, the first time that anybody had ever done this. The flow field around this X-24 was covered with about close to 500,000 grid points in a finite difference calculation. I'm going to show you some results. When I show you these results again, think in your mind, full Navier-Stokes calculation, all the terms of the equations, hypersonic flow, Mach 6 approximately, and let's see what kind of results we get. Figure 817, for example, gives the shear stress directions along the surface of the body. You might call them kind of like streamline directions, or really shear stress directions on the surface of the body in this complex three-dimensional flow. In this picture, we are looking only at half the body. In other words, it's been sort of sliced half. We're only looking at one half of the body, so you only see two of the tails. In a sense, this is the wing, two of the tails. Let's look at some other data. These data are not in your book, but I have to show them to you anyway. Here is a color graphic showing the surface pressure distribution over the X-24 as calculated from these Navier-Stokes calculations, showing what you would expect. A relatively constant pressure along the side of the X-24, peaks in pressure in the nose region and the canopy region, along the leading edges of the tail and the leading edges of the wing. Typical kind of pressure distribution. The heat transfer distribution kind of goes hand in hand. This is the heat transfer distribution. If you think back on our heat transfer equations we were looking at a little while ago, there's a density in there, and that goes with the pressure. And so the heat transfer kind of goes with the pressure. And we see the same thing. We see high heat transfer in the nose region, the canopy region, the leading edges of the tail, the wings, relatively constant heat transfer along the side. Now, let's look at some other data. And again, what we'll be doing here, we'll go back to our X-24, and we're going to be looking at data where I'm going to really cut the X-24 in planes that are perpendicular to the longitudinal axis. I'm going to come down here, like for example, I'm going to take right here in the canopy region, I'm going to cut it with a perpendicular plane. And we're going to look at the Mach number distribution in that perpendicular plane. Just in the canopy region. And what this is, these are contours of Mach number in this perpendicular plane just downstream of where the canopy is in the X-24. This is the outer edge of the shock wave, this is the envelope of the shock wave, and these different colors, of course, correspond to different local Mach numbers in the flow. As we go further downstream, we'll cut the body now, say maybe about here, and there are the Mach number contours that we would see. Again, all of this is coming from our Navier-Stokes solution. If we go further downstream, let's now cut the body right about here so we can get a little bit of the wing in the cut. So we'll cut it right about here. And this is what we get. See the wings now coming up into the picture. These are our contour plots of the Mach number, again showing the envelope of the bow shock wave. And then finally, let's cut it downstream so that we include not only the wing but the tail surfaces as well. And that's what we have here, the Mach number contours on the back end of the body. So once again, what we're looking at here is a rather historic calculation. First time that a full Navier-Stokes solution has ever been carried out for a full airplane configuration, carried out by Joe Shang at Wright Field. Happens to be a friend and colleague, a classmate of mine from Ohio State. And what this represents, we go back to our roadmap, and I'm going to put our roadmap on top here just for a minute. What this represents is the epitome of modern computational methods, Navier-Stokes solutions. Now today, as we speak, these types of full Navier-Stokes equations or solutions are being made more and more frequently. And, but yet, for our purposes here, this represents a reasonable example of what is meant by modern CFD calculations applied to hypersonic flows. Now with that, we're going to switch gears a little bit. And we're going to move finally to the third part of our roadmap. High temperature flows. We have, in this period, we have about 25 minutes left. We're going until 3:55. And in the next 25 minutes, I'd like to make some inroads into discussing some aspects of high temperature flows. And in particular, we're going to spend some time talking about some basic physical chemistry. Now we have to do this, talk about basic physical chemistry, in order to understand what's happening to our hypersonic flows when we encounter these high temperature flows over hypersonic bodies. What we're going to be talking about is covered in your book under Part 3, High Temperature Gas Dynamics. So again, our orientation here now will be for the kind of the following. We're interested in calculating high-speed hypersonic flows over bodies. And we know in real life, kind of what we indicated here in our slideshow earlier this morning, that we're going to encounter high temperatures in these flow fields. And so we're going to have high temperature chemical reacting flows over these hypersonic vehicles. And if you don't take into account properly these high temperature chemical reacting flows, your calculations and even your intuition on things can be way off in terms of what's going on in that flow field. Now, in order to understand what's going on in this high temperature flow, we have to look into a little bit of the physics and chemistry of what's happening. So for the next 25 minutes or so, grab hold of your seats, depending on how much physics and chemistry you feel comfortable with, and we're just going to hit some of the highlights of the physical chemical properties that influence high temperature hypersonic flows. To kind of get things started, let me point out something. Let's kind of go through a thought experiment. And we're going to see this on page 374. I'm looking at figure 912. Let's go through the following thought experiment. Let's look around. You look at the let's look at the air here in the room around us, or wherever you are. Look at the air in the room around you. Let's go through the following thought experiment. Let's take this air. Let's start heating it up. If we start heating it up, higher and higher temperatures. If we look at figure 912, the first thing that's going to happen is that about 800 degrees Kelvin, the vibrational energy in the gas associated with the gas molecules is going to become important. We're going to talk about that in a minute, is what we mean by the vibrational energy. Now, as we continue to heat the air, keep the pressure constant in 1 atmosphere, heat it up to a higher temperature. As soon as we hit about 2,500 K, around 2,000 to 2,500 K, the oxygen is going to begin to dissociate in the air. The oxygen molecules are going to be torn apart. Between 2,500 and 4,000 K, the major chemical reaction that's going on is the dissociation of oxygen. By the time you hit 4,000 K, almost all the oxygen has been dissociated. Now, just by chance, at about that temperature, the nitrogen decides it's time to fall apart. The nitrogen decides to begin to dissociate. And between 4,000 K and 9,000 K, the dominant chemical reaction is that of dissociation of nitrogen. Now, finally, by about 9,000 K, the nitrogen is almost completely dissociated. And again, nature does this in a very handy fashion for us. Nature says, well, at this temperature, we're going to start ionizing. And above 9,000 K is where we're going to start stripping the electrons off of the nitrogen atoms and the oxygen atoms, and we're going to have ionization. These numbers are really worthwhile for you to remember. I'm going to go through these again, because this gives you a feeling for when certain things start happening in your hypersonic flow field. Between up to about 2,500 K or 2,000, between 2,000 and 2,500 K, there are virtually no chemical reactions in high temperature air, but you will have some vibrational excitation. Between 2,500 and 4,000, you're going to get your oxygen dissociation. Above 4,000 K, the nitrogen will begin to dissociate. The oxygen is all dissociated, the nitrogen begins. At 9,000 K, the nitrogen is almost all dissociated, and the ionization begins. Now this has an impact on our velocity-altitude map. Let's go and take a look at that.
Dr. Anderson,
Question,
what
yes.
effect does pressure have on that?
Oh, very good question. Let's go back. We're going to go back to figure 912. Very good question. If we increase the pressure, say like to 100 atmospheres, instead of 1 atmosphere, 100 atmospheres, all of these temperatures will be shifted upward. That is, the temperature at which oxygen will dissociate will no longer be at the beginning 2500 K, it might be 3500 K. Let's go in the opposite direction. Well, okay, we'll say as we increase the pressure, these temperatures for these threshold levels increase. And what that means is if we're sitting here, let's say we're sitting here at 3000 K, at 1 atmosphere, we have a certain amount of oxygen dissociation. Then we increase the pressure to 100 atmospheres. The amount of dissociation is going to go down. And what that is, you can almost think of that as you're increasing the pressure and you're squeezing the dissociation out of the gas. You're inhibiting the dissociation. It's a good question to ask because it becomes important to be able to assess what is happening in your flow fields when the pressure goes up and when the pressure goes down. Very good question to ask. Okay. Let's look at our velocity-altitude map. I had something like this in our slide series this morning. Here we have a plot of velocity versus altitude, the typical velocity-altitude map again. Here we have our flight paths of reentry vehicles on the velocity-altitude map. And superimposed on this now are regions where various high-temperature effects are important. And for example, let's go, we'll kind of repeat what I said this morning. Let's start out here at a low velocity and start increasing our velocity. And the first thing that happens is that vibrational excitation becomes important. And that's because at these lower velocities, your temperatures are too low for dissociation, but they're high enough for vibrational excitation. Now, as we progressively increase the velocity, what we see is that there's a band here where oxygen dissociation is important. And that's because we have this convenient band in here where just oxygen dissociation is occurring. Now, as we fly faster, the nitrogen dissociation will be taking place over this band. And that's because we have this convenient range here where nitrogen dissociation dominates this particular temperature band. And then finally out here, we begin to get ionization if we fly fast enough, and that's because we're now up at these temperature levels where ionization occurs. So this is one place where nature, I think, is really being kind to us by actually separating out these phenomena in a way that's saying that, look, as we go up in velocity, by the time that the oxygen is more or less, let's say by the time the oxygen is more or less dissociated, the nitrogen comes into play. By the time the nitrogen is more or less dissociated, the ionization comes into play. And that you can kind of isolate these different bands just due to these different temperature ranges. Now, yes, good question. Very good question. These temperatures we're talking about and the regions where these reactions are taking place is in the stagnation region. Exactly. Okay, let's take a few minutes and look at some details of from physics and chemistry about gas. Let's just talk about gas properties for a minute. There is definition in physical chemistry called a perfect gas. We've all heard about perfect gases. What's a perfect gas? Here's a let's take the air around us. Let's take a nitrogen molecule, pluck that out, and here's a nitrogen molecule. Okay? Now, surrounding this nitrogen molecule is a force field. It's called an intermolecular force field. It looks like this in figure 10.1. We'll put that on the overhead. The intermolecular force field looks like this. This is the force as a function of distance from the molecule. Way out here, far away from the molecule, is a fairly weak value. It's usually an attractive force. Then as you go in closer to the molecule, it becomes a very strong repulsive force. This is typical of what an intermolecular force field looks like. So let's go back here. Here's our say a nitrogen molecule. It's surrounded by this force field. Now, here's another molecule over here, and it's moving around in space. And in fact, it's the movement of all these molecules that are bringing about the thermodynamic properties of the gas. So here's this molecule is moving around, and in principle it's moving around being influenced by the force field from this molecule right here. This molecule, this force field, is being felt over here by the neighboring molecule. This neighboring molecule is moving under the influence of the intermolecular force field. However, notice again in this figure of 10.1 that the intermolecular force does taper off to a small value. In fact, if you go more than 10 molecular diameters away from the molecule, the center of the molecule, this force field is pretty small and you can neglect it. Now, you can neglect it. By definition, a gas in which you neglect the intermolecular forces is called a perfect gas. That's what a perfect gas means. A gas in which the intermolecular forces are neglected. Now, in this room, if you look at the average spacing in between molecules, right now at standard atmospheric conditions, the mean separation, the mean distance between molecules is a lot bigger than 10 molecular diameters. And so the gas in this room is behaving like a perfect gas. And that's why we can always deal with this type of gas as a perfect gas. Now, keeping that in mind, there are various ways that we serve to classify, that we can use to classify different gases. This starts in section 10.4, page 387, classification of gases. And our first classification is that of called a calorically perfect gas. This is on page 388. A calorically perfect gas. What is a calorically perfect gas? A calorically perfect gas is one where the equation of state is PV equals RT, which we're familiar with, where the enthalpy is a function of temperature given by the specific heat times temperature, and where the specific heats are constant. That's the key. Constant specific heats. You see it there on the monitor, constant specific heats. That's what a calorically perfect gas is. Now, a second type of gas is a thermally perfect gas. By definition, this is one where intermolecular forces are negligible. It's still a perfect gas. PV is still equal to RT because we're neglecting intermolecular forces. In this case, the specific heats now become functions of temperature. That's what is meant by a thermally perfect gas, one where the specific heats are variables, functions of temperature only. Okay? Now, third classification. A chemically reacting mixture of perfect gases. And what this is that we have our gas, maybe it's a gas mixture, it's at a high enough temperature, chemical reactions are taking place. But it can still be a perfect gas because these particles can still be separated far enough away that the intermolecular forces are not exerting any influence. So what do we have? A chemically reacting mixture of perfect gases. The equation of state on page 390 for a chemically reacting mixture of perfect gases is still PV equals RT. The only difference is now that R, the specific gas constant, becomes a variable, but still PV equals RT. Our specific heats now become functions not only of temperature but of pressure also. And therefore the enthalpy and the internal energy becomes functions of pressure in addition to that of temperature. But this is still a chemically reacting mixture of perfect gases. Now finally, our fourth category is that called a real gas. A real gas is one in which the intermolecular forces now become important. You can't ignore them. The particles are packed in closely together and the intermolecular forces are important. That means the equation of state is something like this. You can no longer say PV equals RT anymore. Equation of state is given by something like the van der Waals equation or any of the other thousands of equations of state that have been proposed to account for intermolecular forces. Here, the specific heats are functions of temperature and pressure also. Doesn't involve a chemically reacting gas. It's just a gas, a real gas, where the intermolecular forces are important. A real gas where the intermolecular forces are important. And that's what we mean by this definition of a real gas. Now, so we have four categories: calorically perfect gas, thermally perfect gas, chemically reacting mixture of perfect gases, and a true real gas. These categories are the way that these different types of gases, this is the way that's generally defined in classical physical chemistry. They go way back. If you run down the hall to your friendly physical chemist and you say, tell me about a real gas, the physical chemist will tell you, gee, that's a gas with intermolecular forces and you're going to have to use a van der Waals equation of state or something like that. Now, here's a little bit of semantics. In aerodynamics, the aerodynamicists have screwed this nomenclature up. And what's happened is this. In the early 1950s, when we started thinking about hypersonic flow, and everybody recognized that we're going to have high temperatures in these hypersonic flows, and everybody recognized that we're going to have these types of effects happening. And we'll go back to figure 912 here. That we're going to have vibrational excitation of the molecules, that we're going to have dissociation taking place in the air. This is what really happens in real life at high temperatures. At 4,000 K, you really have almost all the oxygen dissociated and the nitrogen beginning to dissociate. That's a real life effect. And so the aerodynamicists started calling these effects real gas effects because they really happen. They're real life. But what you're really dealing with here, when you get these chemical reactions, is a chemically reacting mixture of perfect gases. And in this range here, PV still equals RT, just R is a variable, because the molecular weight of the gas is a variable. And so when you go down to your friendly physical chemist, and you say, and you want to talk to your physical chemist about how to handle the chemically reacting flow over a hypersonic vehicle, and you may be talking about a flow field where the temperatures might be 5,000 K, and you're deep in this dissociation region, and you run down to the hall to your friendly physical chemist, and you say, man, I've got a problem. I'm dealing with real gas effects. That physical chemist is immediately going to look at you and going to think intermolecular forces. Where do intermolecular forces become important? They become important when the molecules are all packed closely together at high pressures, or 100 atmospheres or 1,000 atmospheres. That's where real gas, true real gases are important. And so what I'm saying here is this, that you encounter some inconsistent nomenclature, and I have to blame the aerodynamicists for this. What I've just said is, I've outlined in red on page 391 here for you. For those of you who have the book, I'd like you to check this and read it later on at your leisure. But what I'm saying is this, instead of reading it to you, I'll just repeat it, that what we're talking about here are high temperature effects, and we're going to be dealing with dissociating gases, chemically reacting gases, in high temperature flows. But all of these, 99.9% of all of these flows can be analyzed on the basis of a chemically reacting mixture of perfect gases, where PV equals RT, and you do not include any intermolecular force effects. This is what, in aerodynamics, is called real gas effects. But I really discourage the use of that term because it's contradictory to what is done in classical physical chemistry. So I will never, from this moment on, use the word real gas effects, because what they are really are high temperature effects. So from this moment on, I will always use the word high temperature effects, and I encourage you to do the same. And I've been saying this for years. It's like a voice crying in the wilderness, and the aerodynamics community still goes on calculating real gas effects, not really meaning real gas effects. So anyway, it's just a matter of semantics, and it's something to think about. What are we going to be talking about? Let's go back to our roadmap. We're still talking about some basic physical chemistry. We want to advance, we want to creep up here on talking about high temperature flows. Before we can do that, we need to talk about some basic physical chemistry. We're starting to do that, and we're still doing that. To go any further, what we've got to do is realize that a molecule moving around in a gas has various different types of motion and energies. Let's go back to the air in this room. Let's pluck out once again this nitrogen molecule, and let's watch it. This nitrogen molecule is moving around in space. Now, that means it has velocity. That means it has kinetic energy. And if we look on our monitor here on page 416, what I have here is a picture, not that picture, get a clean piece of paper here, picture of a diatomic molecule. And this diatomic molecule is translating around in space, and therefore it has translational energy. Now, look back to me for a minute. Here's this pen. This is our diatomic molecule. At the same time it translates around in space, it can also rotate. It can be rotating as it's translating. Therefore, this diatomic molecule has rotational energy. Now, back to me for a minute. Here's this diatomic molecule. 2 nitrogen atoms linked together to make the nitrogen molecule. As this molecule moves through space, these nitrogen atoms can kind of vibrate back and forth relative to their equilibrium position along the internuclear axis. And this vibrational motion has energy. It's called the vibrational energy. The vibrational energy. And finally, if we look at the nucleus of each one of the atoms, there are electrons in motion around the nucleus, and these electrons have energy, and so we can talk about the electronic energy of the molecule. The bottom line of this is that whenever we talk about the energy of a molecule, we must talk about the energy as being the sum. We see this on page 417, as being the sum of the translational energy plus the rotational energy plus the vibrational energy plus the electronic energy of the molecules. Now, next thought. These energies, these molecular energies, are not any old values. They are quantized. They are values that can only be very specific values as predicted by quantum mechanics. We're looking here at figure 11.2. And we're looking at, boy, that really shows up on the monitor, doesn't it? Kind of neat, like an interferogram. The translational energy levels are quantized. The rotational energy levels are quantized. The vibrational energy levels are quantized, and so are the electronic energy levels. This means that when I pluck this nitrogen molecule out of the air and I look at it, it doesn't have any arbitrary value of energy. Its translational energy must correspond to one of these levels. This rotational energy must correspond to one of these levels. This vibrational energy must correspond to one of these levels, and so forth. It's quantized. The energy is quantized. So that's a concept that's important to realize. Next concept. Let's look at this energy level diagram and realize that around this room we have zillions of molecules. As a matter of fact, in a little cubic centimeter at standard atmospheric conditions, we have about 2 times 10 to the 19th molecules. There are a lot of molecules. That means if we take this little cubic centimeter and ask ourselves, how many of those molecules have this rotational energy level? Then by definition, the number of molecules that are in this energy level is called the population of that energy level. If I look at the number of molecules in this energy level, it's called the population of that energy level. So on and so forth. So that when we look at these energy levels, at the same time we've got to visualize that all these energy levels are populated by a certain number of molecules. Now, we skip a lot of pages in your notes, and we come to page 429. Now I'm going to show you an equation that tells you what the population of these energy levels are. It's called the Boltzmann Distribution. This is the number of particles in the jth energy level. Epsilon is the energy of the jth level. K is the Boltzmann constant. T is the temperature. G is something called the degeneracy of that energy level, and we won't worry about what that is. N is the total number of particles in your system. This equation tells you how the number of particles are distributed over the various energy levels at a given temperature T. It's called the Boltzmann Distribution. And so when we go back to looking at our energy levels, then we'll go back to this picture. We visualize that the particles are distributed over these energy levels. If the gas is in what we call equilibrium, these particles are distributed according to a Boltzmann distribution, and there is the Boltzmann distribution. Now, we're going to stop there for a minute. We're going to take a 10-minute break and come back at 4:05, and we will resume our discussion of high temperature characteristics.